Hey guys, welcome back to chapter 15. I'm about to show you the last of the simplified ways to solve these really extra hard ice problems. So up until now, I've showed you how to use the quadratic formula. So we fill out the ice table, we have x's and x squareds. We put it into the quadratic formula format, plug it into a calculator, and it gives us the x. We've looked at perfect square. So if the setup gives us squared on the top and squared on the bottom of that fraction, then we can just square root the whole thing, and that gets rid of the x squared value. The last one is something called a simplifying approximation. So this one's going to feel really odd at first, but I'm going to prove to you why it works. And then I highly advise that this is the method you use after I test you and into the next chapter. I highly advise you use this in the next chapter. But I'll teach you how to use it now so that we can round out our tool belt here and have 3 options to solve these. So a simplifying approximation. We can make an approximation that simplifies the calculations without any significant loss of accuracy. So what I'm going to do now is I'm just going to set up this k value, and I'm going to show you where we simplify or how we make these approximations. Okay. So the k value for this problem, so remember going back that this is A makes 2b. So k equals our products over our reactants. So k equals, and we'll plug in what we know from this table. Okay. So on the top, we're going to have 2x squared, and on the bottom, we're going to have 1 minus x. Okay. And then we would have a value for k. Let me just make something up. Let's say this is 0.06. I don't know. Just making that up. Okay. So our options to solve from here. Well, we could use the quadratic equation. So simplify this out, get into the 0 equals ax squared plus bx plus c, and then plug in a, b, c into the quadratic formula. So again, that one will always work. This is not a perfect square, so I cannot use that because this down here is not squared. Taking the square root of this guy right here is actually really, really challenging and really difficult. It would make it harder than the quadratic formula. So we cannot use the perfect square because this value is not squared. What the simplifying approximation tells us is that if the k value is small enough, and we'll see what small enough means. If the k value is small enough, what we're going to do is we're actually just going to ignore whatever x is added or whatever x is subtracted. So wherever you see the number minus an x or the number plus an x, that's going to be the x that you just get rid of. Simplifies it, right? We'll come back around and prove this to ourselves that it works. But for right now, that's what we're going to do. So when I simplify this particular problem, then what we see is 0.06 equals, on the bottom, we're just left with the number 1, and then distribute this squared through, that's 4x squared. Okay. Now simple algebraic rearrangement, and I can solve pretty easily for x. So that's what the simplifying approximation is it just simplifies it by getting rid of an x added or subtracted. Okay. What makes this something that's valid? So this is a validation that you're going to have to do to make sure that you can use this simplifying approximation. So once you determine what x is, the number that is subtracted should be less than 5% when we put it into a ratio. So I know those are words and words are hard. So let me put this on paper. So to validate x is small. So to validate and make sure that we didn't lose anything by doing this, we're going to do the following. We're going to use the x that we solved for. We're going to put it over the number that it was subtracted from or added to. Okay. We're going to multiply that by 100, and this needs to be less than 5%. So we're multiplying by 100%. Okay? So the x that we solved for divided by the number that we cut it away from times 100, and that needs to be less than 5%. And if it's less than 5%, then we can say x is small is valid. We're able to use it. Okay? So again, best way is just to dive into a problem. So let's dive into a problem. So here's our example. Consider the following reaction. Notice that our Kc value is really, really small. That's a good sign. That's good news. The reaction vessel initially contains 0.052 molar of the reactant. We want to know what is the concentration of our products. Okay, so let's set up our ice table here. Okay, so the textbook provided us with an ice table. So we've got our reactant. I'm going to put our helpful 2. Well, it's not helpful when it's green on blue. I'm going to put our helpful 2 in there. So we don't forget to multiply it by 2. I'm going to put our helpful 2 in here so we don't forget to multiply that by 2. All right, so initial for our reactant products, there's no mention of the initial. We're going to keep those as 0. Okay. No mention of the equilibrium concentration, so we're going to have to fill this table out with a bunch of x's. So our products are going to go up by a factor of x and a factor of 2x. And our reactant is going to go down by a factor of 2x. So at equilibrium, we'll have 0.025 minus 2x. What a mess. 2x and x. Okay. So let's put in our K equation now. Okay. So K is 1.67 times 10 to the negative 7th. Oops. We're going to do products over reactants. So our products were 2x and x. So we're going to have 2x squared x. And our reactants were this guy right here. So we're going to have 0.025 minus 2x, and that is squared. Okay. You are going to want to use the perfect square here because you see 2 sets of squares. But remember, you've got this other x over here. So he kind of ruins it all for us. So we cannot use the perfect square. But let's see if we can use the x is small approximation. So that's what I call it, is x is small approximation. So I'm going to assume that by subtracting this number right here, it's not really going to affect the calculation much at all. So I can simply ignore that portion of it, and I don't have to worry about it. I can just kind of get rid of it, okay? So by using that x is small approximation, here's what we're left with. We still have this. On the top, we still have 2x squared times x. And on the bottom, we're left with 0.025 squared. Now the algebra is pretty easy to solve for x. So cleaning up this top, let me do that first. 2x squared is 4x squared. Okay. And if I multiply that by another x, remember that we add the exponents. So on the top, we've got 4x cubed. On the bottom, I just need to type this in. So 0.025 squared is 6.25 times 10 to the negative 4. And we still have this over here. Okay. Now let's do some algebraic rearrangement. First, get rid of that denominator. That cancels. Whatever I do to the left side, I also have to do to the right side. That's a 4. So we're left with 4x cubed equals 1.67 times 10 to the negative 7th multiplied by 6.25 times 10 to the negative 4th. And over here is 1.04 times 10 to the negative 10th. I need to get my x by itself, so I'm going to divide by 4. Those cancel. Divide by 4. So x cubed equals, so 1.04 times 10 to the negative 10 divided by 4. And we have 2.6 times 10 to the negative 11. And what you're going to do here is you're going to take the cubed root, okay? So if you have a TI-8485 calculator, you're going to have to hit the button that says math. So inside of that button, there's a lot more math functions that you can access. So when I hit the math button, it is the 4th one down. So this is what it looks like on my screen. Okay, so that's the cubed root. So I select cubed root. I type in 2.6 times 10 to the negative 11. And so now we get, I'm going to put it over here in a different color just because I ran out of room. X equals 2.96 times 10 to the negative 4. So what we've done so far is we assumed that x is small, and we're about to validate that. So we got rid of this piece. Then we used algebra to solve for x. What we have left is to validate, and then ultimately we need to finish the problem and determine the equilibrium concentrations. Okay? So now let's validate this. So remember the validation is we're going to take x divided by the number it was subtracted from and multiply that by 100%. Okay? So x is this guy right here. So to validate, I'm going to take 2.96, make sure I didn't get dyslexic, good, times 10 to the negative 4th divided by, so what number did we what number was it originally subtracted from? It was originally subtracted from this 0.025. So I'm going to divide it by 0.025, multiply that by 100%. And we're going to see if this is valid. So 2.96 times 10 to the negative 4th divided by 0.025 times 100%. And I get that this is 1.2%, which is less than 5%. So it is valid. So what we just proved is that x is small did in fact work, okay? So let's talk about what x is small means. What we're saying is that x is so small, this right here, is so small that we take 0.025 minus 2x, and it is not going to change that number significantly at all. So if we think about this as being 0.025000000, it's not going to change this number until we get to the 1, 2, 3, 4, until we get to the next fourth or fifth decimal place. That's where it's going to start to change this number. So what x is small is relying on is the fact that 0.025 is basically the same as, and let me go ahead and subtract it. So it's saying that 2.05 is essentially the same as 0.029999994. Okay, so when I put this in my calculator and I actually use x, this is the number that we would have used in our equation. And what x is small approximation is telling us is these two numbers are so incredibly close to one another, close to one another that this doesn't even matter. It doesn't change the outcome. Okay, so that's what x is small is relying on. That's what it's based on. Okay, so x is small is valid. Now we have our value for x, and now we can complete our problem. So our problem wanted to know what is the equilibrium concentrations of our two products. So the equilibrium concentration for S is just the 2.96 times 10 to the negative fourth. And the equilibrium concentration for H is 2 times that value. So 2 times 2.96 times 10 to the negative 4. So equilibrium concentration for hydrogen is 5.92 times 10 to the negative 4. Okay. Lots of information there. So here's what the big take home is. X is small will work if Kc is a relatively small number. So times 10 to the negative 7th, that's a small number. X is small approximation is essentially taking any x value that's added or subtracted, and getting rid of it, ignoring it, saying, yeah, that doesn't really exist anymore, okay? Solving the problem and solving for x at that point, okay? The one extra piece that you have to do is just make sure that x is small is valid. Make sure that you can use it. Make sure that when you make the assumption that it's not going to change the problem, that it doesn't actually change the problem. So that's the one extra step, is you do have to validate it to make sure that it works. But other than that, it makes your life so much easier. I hope you guys found this helpful.